Today we're going to work through a simple spring problem. The problem states a 5 kilogram mass is hung from a spring with a rest length of 30 centimeters. If the spring stretches to a length of 40 centimeters when it comes to rest, what is the spring constant of the spring? And B, if the spring is stretched another 5 centimeters, what will the mass's acceleration be when it's let go? So we're going to start by drawing our free body diagram. We have our mass. Draw it farther down. Hung by a spring. It tells us the rest length of the spring is 30 centimeters and that the spring is stretched to a length of 40 centimeters. Now we can diagram the forces acting on it. We have a gravitational force between the mass and the Earth. And we have the spring force between the mass and the spring. And then we're going to assume here that our spring is massless. Now, in part A of our problem, it says this is what happens when the mass comes to rest. So we can assume that for part A, the acceleration equals 0 if it's at rest. And our mass is in equilibrium. We can write a Newton's second law equation for this. So it's the sum of forces. We only have one direction here, I'm going to call up positive. It is equal to the spring force minus the gravitational force. This is going to equal 0. Which tells us the spring force must be equal to the gravitational force. Now this problem asks us for the spring constant of the spring, so we have to use a couple more equations that relate the gravitational force to the mass and the spring force to the spring constant and how it stretches. So if you remember from class, our formula for gravitational force, if we use the local version, is gravitational force equals m times g. And in this case, our m is 5 kilograms, and we'll assume on Earth with a gravitational constant of 10 newtons per kilogram, which gives this thing a weight of 50 newtons. Which tells us that if we use this with our Newton's law equation, that both of these forces must be 50 newtons. We can then move on to our spring equation, which says the force from a spring equals, I'm going to leave the negative off because I already took care of that in my free body diagram. And the negative just tells you the direction the force is applied. So I want to say the spring force equals K times delta X. Now the tricky part here some kids always get tricked up on is this is delta X, it's not X. So the spring, yes, is stretched out to 40 centimeters, but delta X in our picture is actually the difference between the rest length of the spring and the actual stretch length. So there is delta X. In this case, we can easily see that delta X equals 10 centimeters, but remember, we're using newtons, we're using constants here, especially the gravitational constant, so we want our distances all to be in meters, so this would be 0.10 meters. Make sure we use that when we do calculations. We can solve our spring equation for K. K equals the spring force divided by delta X, and now we just plug in our values. We've got 50 newtons for the spring force. Delta X is 0.10 meters, and we get a spring constant of 500 newtons per meter. Part B asks, if we stretch the spring another 5 centimeters, so it's already stretched 10 centimeters, so part B is telling us that our delta X now is going to be equal to 15 centimeters, which is equal to 0.15 meters. So if that's the new case, it wants to know what the acceleration of the system is. So again, we can write a new Newton's law equation for this. I'm not going to redraw the free body diagram right now, but it's basically our spring force should get bigger by a little bit. My delta X is also going to get bigger. Our new Newton's second law equation says that the sum of forces is still just the spring force minus the force due to gravity, but instead of being equal to 0, this situation is no longer in equilibrium, so it equals m times a. We can now at this point, we don't want to resolve the entire problem. We can use a lot of stuff. We already found the gravitational force. We don't need to find that again. We know the the mass of the object. We also know the spring constant we found in part A, so we can use that in part B. So I'm going to substitute our equations for the gravitational force and for the spring force into this new. And I'll substitute any values that we have. So the spring force we don't have yet, but we know that it's going to be K times delta X. minus the gravitational force, which is 50 newtons, is going to be equal to the mass of this object, which is 5 kilograms, times the acceleration of the system. So again, we're looking for the acceleration. I can now plug in some other values that I have. I can use K from part A, so I have 500 newtons per meter times 0.15 meters minus 50 newtons is going to equal 5 times the acceleration. Now it's just doing a little math out. We have 50 times, or 500 times 0.15, which gives you 75. 75 minus 50 is 25 newtons, and that's going to equal to 5A. Therefore, our acceleration of our system here, and it's just 0.15 centimeters, with the 5 kilogram mass hanging on it, is going to be 5 meters per second squared. So again, even though spring force is a little bit weird looking force, it's nothing really different. It's still just a force. It still shows up in the free body diagram just like everything else. The only difference is we have this special equation here, kind of just like friction related to the gravitational force, that you can use to find it if we need to.